Hello everyone, my name is Lika Fai. My metric number is 224303. Today I'm going to present about the topic which is fluid feature and dimensional analysis concept for this individual assignment. So these are the topics that we are going to be discussed today. First, let us discuss about fluid feature. So what is fluid? Fluid, it can be liquid or gas or generally any material that cannot sustain a tensional or shearing force when at rest. It also the substance that undergoes a continuous changes in shape when subjected to such a stress. It also designates all matters composed of molecules that attract each other through a very big force of attraction. So, since fluid is considered as gas or liquid, let us look at their characteristics. First, gas. Gas is considered as loosely associated molecule. It travels through space for long distance. The velocity of their travel depends on the temperature of the gas. And lastly, liquid. Liquid is considered as molecules that are very close together, in collision with each other very frequently. The velocity of their motion and the rate of their collision depend on the temperature of the liquid. So there are many types of fluid, but I want to discuss about 5 fluid first. Firstly, real fluid. It is viscous or compressible. The position of their molecule can change continuously. Secondly, Newtonian fluid. Their viscosity is constant for different rates of shear and does not change with time. Their behavior can be explained by Newton's law of motions. Superfluids. It flows under the slightest force applied to them without any resistance or friction. Non-Newtonian fluid. This does not have a unique viscosity because it varies with the rate of shear or varies with time. It depends on the forces exerted of them as well as temperature changes. And lastly, dystrophic fluid. It becomes thinner and less viscous as they continue to be stirred. So let's look at the example of fluid. There are 3 fluids that I am going to introduce today, which are blood plasma, helium, and mercury. Firstly, blood plasma. Blood plasma is a non-Newtonian fluid whose viscosity increases with applied shear stress but which stops increasing progressively as velocity increases. Helium. It lacks viscosity and is considered a superfluid. Mercury. It is a Newtonian fluid, the only liquid material at room temperature. The fluid feature that I'm going to discuss today is such as density, viscosity, pressure, temperature, compressivity, surface tension, flow characteristic, and temperature. So, firstly, let's look at density. Density means mass per unit volume of a liquid, fluid. It is a fundamental property that affects buoyancy, pressures, and fluid dynamics. It can have a higher or lower density, depends on the amount of matter in the fluid volume. The SI unit of density is kg per cubic meter, while US customary unit is slug per cubic feet. So next, let's look at the viscosity. Viscosity means measure of a fluid resistance to deformation and flow. It plays a crucial role in determining the flow characteristics of liquids. It resists both the relative movement of immersed object and the mobility of layer with different velocity inside them. It determined by the state of a fluid, which includes temperature, pressure, and deformations. In some circumstances, the reliance on some of these features is minor. Let's look at pressure. Pressure is the force exerted by the fluid per unit area. It varies with depth in the fluid due to gravity and is the key factor in fluid static and dynamics. For instance, the pressure on the seabed is much higher than on land. The SI unit of pressure is Pascal, while US customary unit is pound force per square feet. At the bottom is the force, the formula of the pressure, which is P equals to F divided by A, where P is pressure, F is force applied, and A is area. So let's talk about temperature. Temperature is measure of hotness or coldness expressed in terms of any observable laboratory scales. It's indicating the direction in which heat energy will spontaneously flow from a hotter body to a colder body. It affects fluid properties such as density and viscosity. It influences the behavior of fluids in thermodynamic processes. The SI unit of temperature is Kelvin, while US customary unit is British thermal unit. Next, let's look at compressibility. Compressibility is measure of the change in volume of the fluid under pressure. Liquids are generally incompressible while gases are compressible, since the fluids are categorized as liquid and gases. The compressibility requires a proportional decrease in volume when pressure within the constant mass of fluid increases. It is widely used in the domain of fluid dynamics and thermodynamics, and it is essential to understanding how material behave under various conditions. Alright, so let's look at surface tension. Surface tension is a cohesive force at the surface of a fluid that causes it to behave like the stress elastic membrane. It is significant in phenomena such as capillarity. It depends upon the force of attraction between the particle within the given liquid and also on the force of attraction of solid, liquid, or gas in contact with it. The SI unit of surface tension is Newton per minute, while CGS unit is Din per centimeter. So I will talk about flow characteristics. Flow characteristics describes the behavior of fluids in motions, including laminar and turbulent flow, which is essential for understanding fluid dynamics. Laminar flow is smooth and orderly, while turbulent flow is chaotic. The picture below shows the movements of both flow. So this is the last fluid feature that I'm going to talk about is buoyancy. Buoyancy is upward force exerted by the fluid on an object immersed in it. It explains why objects float or sink. It's the concept of the force is used to explain buoyancy. Gravity. So just think about that gravity is a downward force that acts on all objects. When objects are placed in the fluid must supply a force equal in magnitude but opposite in directions to the gravitational force for the object to float. This force is referred to as the buoyant force. Okay, after finishing the fluid feature, let's talk about dimensional analysis. So what is meant by dimensional analysis? Dimensional analysis is amongst the most valuable tool physical scientists use. Simply put, it is the conversion between an amount in one unit to the corresponding amount in the desired unit using various conversion factors. Dimensional analysis is also essentially a method of using the unit of quantities to help solve problems. It involves converting from one set of unit to another and can be used to check that an answer makes sense. So why do we need to use dimensional analysis? Because it simplifies complicated physical problems. Secondly, it prevents error because the dimensional equations must be dimensionally homogeneous to be physically possible. Thirdly, it can also guide and validate experiments. Using dimensional analysis involves understanding some critical concepts like similarity, prototypes, and models. A great historical example of dimensional analysis in practice is Leonardo da Vinci. Use of models to plan his art. He will often create small sculptures or models as part of his planning process of larger works. There are three dimensional analysis that I'm going to discuss, which are dimensions and units, dimensional homogeneity, and dimensionless numbers. So the first topic is dimensions and units. A dimension is a measure of the physical variables which without numerical values, while a unit is a way to assign a number or measurement to that dimension. For example, length is a dimension, but it is measured in units of feet or meters. There are three primary unit systems in use today, which are the International Systems of Units, the English Engineering System of Units, the British Gravitational System of Units. There are two types of dimensions and units. So let's look at primary dimensions and units. Primary dimensions are defined as independent or fundamental dimensions from which other dimensions can be obtained. There are 7 primary dimensions. The primary dimensions are mass, length, time, temperature, electric current, amount of light, and amount of matter. This is a table of primary dimension with their own primary units. Next, secondary dimensions and units. Secondary dimensions derive as combination of these 7 primary dimensions. For example, power is often expressed in units of British thermal unit per hour, British thermal unit per second, calorie per second, ergs per second, or horsepower, in addition to the standard unit of watt and feet multiplied by pound force per second. There are conversion factors listed in many textbooks to enable conversion from any of these units to any others. This is the table of secondary dimension with their own secondary unit. So let's jump to next topic, which is dimensional homogeneity. Dimensional homogeneity is an equation is dimensionally homogeneous if all terms in the equations have the same dimensions. This principle is essential for the consistency of physical equations. In any equations, each additive term must have the same dimensions. It is useful when checking the algebra of the problem solutions. It also extends to units. Let's look at the example. The area of the rectangle is a product of its width and its height, which is A equals to WH, where A stands for area, W stands for width, while H stands for height. The dimension of both terms in these equations are length squared. The equation A equals to H is clearly wrong, which is it is dimensionally inconsistent since the dimensions of the left term are length squared, while those of the right term are length. Therefore, the best way to avoid unit errors is to list the units along with any numbers supplied to an equation. Also, it is best to introduce conversion factors in the form of ratios. So, here is the example questions. Suppose the width W of the rectangle is 48 inches and the height H is 2 feet. The area A is desired in square feet and is calculated correctly as follows. A equals to WH equals to 48 inch times with 2 feet times with 1 feet per 12 inches to convert each into feet. And the answer is 8 square feet. Let's look at the last topic, which is dimensionless numbers. Dimensionless number is the ratio of quantities that have no units and are used to characterize the different physical situations. These numbers often reveal fundamental similarity between different physical systems. For example, Reynolds number, Freudian number, and Mach number. The figure shows that the formula of each dimensionless number, which are Reynolds number, Prandtl number, and Nusselt number. So how can we apply dimensional analysis? First, we can use it to check the consistency of the dimensional equations. Secondly, we can use it to derive the relation between physical quantities in physical phenomena. And lastly, we can use it to change unit from one system to another. The figure shows that the questions uses the dimensional analysis to check the correctness of the physical equations. Sadly, there are some limitations that we need to consider while using this dimensional analysis method. Firstly, it does not give information about the dimensional constant. And secondly, the formula containing trigonometric functions, exponential functions, logarithmic functions, etc. cannot be derived. And lastly, it gives no information about whether a physical quantity is a scalar or vector. These are the reference for fluid features. These are the reference for dimensional analysis. Both of them consist of journal, books, internet, and many more. Thank you everyone for watching.